Anytime a mass or an object is separated from the Earth or its vertical position is increased, we say that the mass or the object and the Earth together are storing gravitational energy. So if the separation is increased, there's going to be an increase or change in gravitational potential energy. What we want to be able to do is quantify or figure out how much gravitational potential energy do you store when you separate a mass from the Earth. You might also ask, kind of useful things can we do by separating masses from the Earth or storing gravitational potential energy? One of the neatest examples I've seen of this was a recent development by two engineers who sought to provide some kind of lighting solution for developing countries. With developing countries or villages that don't have a ready supply of electricity, lighting is a big issue, and oftentimes they use kerosene lamps for light when the sun goes down. The issue with this is the smoke that it gives off leads to a lot of health problems, and so there's a really big need for lighting that doesn't involve burning something. Batteries and solar panels sometimes work, charging batteries and then using that charged energy to power some kind of light works, but batteries are expensive and they need to be replaced. They have a limited lifetime. So this is a unique solution that these engineers came up with, where they just basically filled a bag full of rocks and sand, and this bag was raised to some vertical position above a height of 0. It's attached to some kind of plastic, kind of like cable, and as this thing slowly lowers back down to the Earth, it spins a generator inside of the housing, and that generator produces electricity enough to power a small LED light for about 25 minutes. So adding gravitational potential energy to this mass stores that energy. That stored energy is then used to actually produce light. There's no batteries involved, so there's no reoccurring cost to buy batteries when they go bad. The only thing you have to do, it literally takes seconds, is to raise this mass up. So let's see if we can come up with an equation to figure out how much energy is stored by some mass m that's raised to some height y. So in order for this mass to be above the ground, something has to do work on the mass, transfer energy into the mass in the Earth as a system, and that energy transferred into the mass Earth system is stored as gravitational potential energy. So the amount of work done, which we know is equal to the amount of force used times the displacement, as long as that force is in the same direction as the displacement, and all of that energy is going towards gravitational potential energy. Well, all we need to do is figure out how much force do you need to use and what is the displacement, kind of given the variables that we have. So if you need to lift a mass up, every mass has a weight, which is just equal to the mass times the gravitational field strength of the Earth, or mg. You have to lift with at least that much force. If you were to move this thing up at a slow constant velocity, you'd have to use a pushing force or a pulling force equal to the weight, equal to mg. So if you use a force equal to its mass times gravity, or mg, over some displacement or over some change in vertical position, the amount of work done, which is also the change in gravitational energy, would be equal to mg times delta y, or your change in vertical position. Let's look at an example problem using this idea. So the amount of stones or sand that gets put in there is about 9 kilograms, and let's just assume that it's raised up to some height of 1.5 meters above the ground. We'll say the ground is a height of 0 where it doesn't have any gravitational potential energy, and let's say it's raised up so that now it's 1.5 meters higher vertically than it was previously. Well, let's find out how much gravitational potential energy is stored, which can be used to power that small LED. Our general equation for the change in gravitational potential energy is the mass that's raised times the gravitational field strength of the Earth near the surface times the change in vertical position. So if we just plug in the values that we have, 9 kilograms of mass is being raised. The gravitational field strength of the Earth is 10 newtons for each kilogram, and it's been raised up 1.5 meters, and so the change in gravitational potential energy will be positive. If we look at the units, we've got a kilogram times a newtons per kilogram. There's a kilogram in the top and bottom of a fraction, so that can cancel. So we're left over with units of Newton times meters. Remember that a Newton meter, or a Newton times a meter, is a joule. So the change in gravitational potential energy, in this case, for this mass raised to that new height, is 135 Newton meters, or positive 135 joules.